Queuing theory refers to the mathematical study of the formation, function, and congestion of waiting lines or queues. At its core, a queuing situation involves two parts. First, someone or something that requests a service, usually referred to as the customer, job, or request. Secondly, someone or something that completes or delivers the service, usually referred to as the server. To illustrate, let's take two examples. When looking at the queuing situation at a bank, the customers are people seeking to deposit or withdraw money, and the servers are the bank tellers. When looking at the queuing situation of a printer, the customers are the requests that have been sent to the printer, and the server is the printer. Let's understand queuing theory with a more elaborative example. This situation here is of a doctor's clinic. Here, the server would be the doctor and the customer would be his patients. The doctor's clinic comprises of the complete system. The patients waiting outside doctor's office forms the queue length, and if we include the person taking treatment inside the doctor's office, it will compose of the system's length. The people outside doctor's clinic will be termed as calling population or input source because they are the potential customers. The doctor can adjust his schedule accordingly if he knows the rate at which patients come to his clinic, how many people are waiting outside his office, at what time of day the crowd is highest, and many more. So this is where queuing theory steps in. Now there are certain terms that one should know prior solving queuing problems. First is arrival rate. It is the expected time between each customer arriving. The arrival rate is random and it is best described by Poisson's distribution and is denoted by lambda. And service rate is the expected number of consecutive service completion per the same unit time. This is best described by exponential distribution and is denoted by mu. Now queue length and service length as discussed earlier in case of that doctor's clinic example. This queue length and service length can be finite or infinite. And lastly, there is the calling population or the input source. See, it's the population of potential customers, and it can be assumed to be finite or infinite. Next comes the number of servers in a system. It can be a single server, like a single doctor in a clinic, or a multi-server, like ticket counters. There are certain service rules as well, like first come, first serve, first in, last out, service in random order, and priority treatment. And finally, there is customer attitude or behavior. A customer who is patient waits patiently. An impatient customer creates nuisance. A reneging customer joins queue but leaves after short interval. Balking customers are those who enter the system but does not join the queue. And then there are jockeying and cheaters. Jockeys are those who keep on switching queues, and cheaters are those who obviously cheats the queue.